Good morning. Today we will continue with partially ordered set. In previous lecture we had defined partially ordered set. A non-empty set A together with a binary relation R is said to be partially ordered set if the three conditions reflexivity, antisymmetry, transitivity are satisfied. In short we call it post set. We had also learned how to draw Hasse diagram for some of the partially ordered set. We will learn some more example by drawing some more example how to draw Hasse diagram. Now in this example we have a set S equal to A, B, C and the relation is inclusion, means A is a subset of B, and we need to draw the Hasse diagram for the power set of S. S is a set consisting of A, B, C. Therefore power set of S is a set consisting of phi A, B, C, these are singleton sets. AB, BC, AC, these are sets consisting of two elements, and ABC, the set itself. So this is the power set of the given set S. Power set means the set consisting of all the subsets of S. Now we will draw the Hasse diagram of this power set of S, and the relation given to us is inclusion. So first element is phi. We will write phi here. The next element is A. We write A here because phi is a subset of A. The next element is B. We will write B here because phi is a subset of B, but A is not a subset of B. Next element is C. We write C here because phi is a subset of C, but B is not a subset of C. The next element is AB, and we write AB here because A is a subset of AB and B is also a subset of AB, but C is not a subset of AB. Next element is BC, and we write BC here because B is a subset of BC and C is a subset of BC, but A is not a subset of BC. Next element is AC. We write AC here because A is a subset of AC and C is a subset of AC, but B is not a subset of ABC. And we write ABC here because AB is a subset of ABC, AC is also a subset of ABC, and BC is also a subset of ABC. So this is the Hasse diagram of power set of S together with the relation is a subset of or inclusion defined on it. So this is the poset PS is a subset of. Now one more example. In this example, we are given a directed graph for a relation on a set A equal to 1, 2, 3 as shown in figure. And we need to verify that AR is a poset and we have to find its Hasse diagram. Also, we will find the edge which make this diagram to be totally ordered so that AR become totally ordered. So this is a given directed graph, or in short we call it digraph. Here 1 is related to 1, this arrow indicates, 2 is related to 2 indicated by this arrow, 4 is related to 4 and 3 is related to 3. Again 3 is related to 1, arrow is in this direction, 3 is related to 2, 3 is related to 4 and 1 is related to 4. So this is the given digraph. So the corresponding relation is 1 related to 1, 2 related to 2, 3 related to 3, 4 related to 4, 3 related to 1, 3 related to 4, 1 related to 4 and 3 related to 2. Clearly this relation is reflexive because each element of this set is related to itself, means A is related to A for all A belonging to A. 1 is related to 1, 2 is related to 2, 3 is related to 3 and 4 is related to 4, as is clear by these arrows. Hence it is reflexive. If A is related to B and B is related to A, then it is possible only if A is equal to B. Hence it means it is antisymmetric. Also, if A is related to B and B is related to C, it means A is related to C. Here 3 is related to 1, 1 is related to 4. It means 3 is related to 4. Hence, all the three conditions are satisfied. Therefore, AR is a poset. R is the relation which is demonstrated by these arrows in this diagram, and A is this given set. Now we will draw the Hasse diagram. We need to draw the Hasse diagram for this. First element is 1 here. We write 1 here. Next element is 2. We see that 1 and 2 are not related anywhere. It means we will write 2 here. Next element is 3. So here we see that 3 is related to 1. So we write 3 here and we join 1 and 3. Next element is 4. So we see that 3 and 4 are related and 1 and 4 are related. It means we join 1 and 4. And clearly 2 and 4 are not related, so we have not joined 2 and 4. So now we will find the edge that is needed in the figure to extend AR to total order. We see all the elements are related, but 2 and 4 are not related to each other. So if we include the edge 4 to 2, means we join 4 to 2 and this is the arrow in this direction, then it will become totally order. AR which is a poset will become totally order, because in total order we need to satisfy all the three conditions of poset as well as of total order, which means every element is comparable. So if we join 4 to 2, it will make it totally order. Now one more example. Suppose A is equal to 1, 2, 3, 4, 6, 8, 9, 12, 18 and 24. Suppose this is a given set and the order relation A divides B. Now we will draw Hasse diagram for this set. First element is 1, we write 1 here. Next element is 2, we write 2 here, and clearly 1 divides 2. Next element is 3, we write 3 here because 1 divides 3 but 2 does not divide 3. Next element is 4, so it means 2 divides 4 but 3 does not divide 4, so I have written 4 here. Next element is 6, I have written 6 here because 2 divides 6 and 3 divides 6 but 4 does not divide 6. Next element is 8, so I have written 8 here because 4 divides 8, 6 does not divide 8. Next element is 9, I have written 9 here because 3 divides 9. 6 does not divide 9, 4 does not divide 9. Next element is 12, I have written 12 here because 6 divides 12. Next element is 18, so I have written 18 here because 9 divides 18, 6 also divides 18. Next element is 24, I have written 24 here because 8 divides 24 and 12 divides 24. Now this is the Hasse diagram of BQ, where BQ are matrices with 1 row and 3 column, and is defined as matrices of zeros and F's where Rij m by n is less than or equal to Sij m by n if and only if Rij is less than or equal to Sij for all I and j, where 0 is less than or equal to 0, 0 is less than or equal to 1, 1 is less than or equal to 1 and 1 is not less than or equal to 0. It means BQ are matrices with 1 row and 3 column. So 0, 0, 0, 1, 0, 0, then 1, 1, 0, here 0, 1, 0, 0, 0, 1. Clearly 0 is less than 1, so we have written all the 3 zeros here. Then 1 and 2 zeros, 0, 1, 0, 0, 0, 1, then 1, 0, 1, 1, 1, 0, 0, 1, 1, 1, 1, 1. This is easy to draw, because we have used 0 is less than equal to 0, 0 less than equal to 1, 1 less than equal to 1, and 1 is not less than equal to 0. So this is the Hasse diagram of BQ. Now we will define maximal element and minimal element. An element belonging to a point A less than equal to is said to be maximal element of A if there is no element C in A such that A is less than equal to C. Then in this case, A is called the maximal element. An element B belonging to A is called the minimal element of A if there is no element C in A such that C is less than equal to B. Now we will find the maximal and minimal element of process whose Hasse diagram is given to us. Clearly, at looking at the Hasse diagram, we see that 1 and 6 are the minimal elements and 3 and 5 are maximal elements. Now, what is the greatest element? An element A belonging to A is said to be greatest element of A if x is less than or equal to A for all x belonging to A. And this greatest element is also called last element or unit element. We generally denote it by 1. The greatest element is unique if greatest element if exists is unique. It may happen that greatest element does not exist. It may happen that greatest element does not exist. Greatest element is also called universal element. It is also called universal upper bound. So remember one thing, that A belonging to A is said to be greatest element of A if x is less than or equal to A for all x belonging to A. And I again want to remind, it is also called last element or unit element, and we denote it by 1. The greatest element if exists is unique, but it may happen that greatest element does not exist. It is not always possible that greatest element exists. And the least element, an element A belonging to A is said to be least element of A if A is less than or equal to x for all x belonging to A. A least element is also called first element or zero element of A and is generally denoted by 0. The least element if exists is unique. But it may happen that least element does not exist. It is not necessary that least element exists. And the least element is also called universal lower bound. Now the least upper bound or supremum. Let P with a relation less than or equal to defined on it is a poset, and A is a subset of P. An element x belonging to P is said to be least upper bound or supremum of A if x is an upper bound of A and x is less than or equal to y for all the upper bounds y of A. A greatest lower bound if exists is unique, and we denote the this is the least upper bound. Least upper bound if exists is unique, and we denote the least upper bound by LUB and supremum by SUP. And the greatest lower bound, suppose P together with less than or equal to is a relation defined on the set P be a poset, and A is a subset of P. An element x belonging to P is said to be a greatest lower bound or infimum of A if x is a lower bound and y is less than or equal to A x for all lower bounds y of A. The greatest lower bound if exists is unique. There cannot be two greatest lower bounds. Also we denote greatest lower bound by GLB and infimum by INF. Sometimes we call greatest lower bound or infimum, it is one and the same thing. Now we will show that a poset has at most one greatest and at most one least element. Let A and B be two greatest element of poset A. Since B is the greatest element, It means A is less than or equal to B. We have supposed that A and B are two greatest elements. So if A is the greatest element, then we have B less than or equal to A. But A and B are element of possess, so it satisfies antisymmetric properties. Antisymmetric property means if A is less than or equal to B and B is less than or equal to A, then B is equal to A. So there cannot be two greatest element of poset A. So it means poset has at most one greatest element. Similarly, we can prove that the poset has at most one least element. Hence, poset has at most one greatest element, at most one least element. Now we will consider one more example. Consider the set A equal to 1, 2, 3, 4, 5. Define the relation less than on A such that x is less than y if and only if x mod 3 is less than y mod 3. To prove that A less than or equal to is a poset. Now and also we will draw the Hussey diagram for this poset and we will find the maximal and minimal elements. So first of all we will show that this set is a poset together with the relation defined as x mod 3 less than or equal to y mod 3. So we know that 1 is less than or equal to 1 implies 1 mod 3 is less than 1 mod 3. Similarly, we can show that every element of A is related to itself. Hence, it is reflexive. If A is less than or equal to B, it means A mod 3 is less than B mod 3. If B is less than or equal to A, then B mod 3 is less than A mod 3. And this is possible only if A equal to B. A mod 3 less than or equal to B mod 3 and B mod 3 less than A mod 3 is only possible if A equal to B. Hence it is antisymmetric. Suppose A is less than or equal to B, it means A mod 3 is less than or equal to B mod 3 and B less than or equal to C, it means B mod 3 equal to C mod 3. If A mod 3 is less than or equal to B mod 3 and B mod 3 less than or equal to C mod 3, it means A mod 3 is less than or equal to C mod 3. Hence A is less than or equal to C. That is, it is transitive. Therefore, A less than is a poset. Now we will draw its Hasse diagram. So first element in the set is 1. So this is 1 here. 1 mod 3 is less than or equal to 2 mod 3. So this is 2 here. And next element is 3. So I am writing 3 separately because 1 mod 3 is not less than or equal to 3 mod 3 and 2 mod 3 is not less than or equal to 3 mod 3. Next element is 4. So I have written 4 here because 1 mod 3 is less than or equal to 4 mod 3 and 3 mod 3 is less than or equal to 4 mod 3. Next element is 5. So I have written 5 here because 2 mod 3 is less than or equal to 5 mod 3 and 4 mod 3 is less than or equal to 5 mod 3. So this is the Hasse diagram for the set 1, 2, 3, 4, 5 in which the relation is defined as x mod 3 less than y mod 3. Here clearly maximal element is 5 and minimal elements are 1 and 3. Thank you.